Sorry about the audio. I'm sure I hope you can hear me now. Please kindly confirm if you can hear anything. Sorry about the audio. I'm sure Okay, I think it should be sorted now. Okay. So this is what we have been saying. We have a ball dropped. So if it is dropped, it means the initial velocity of that ball is 0. Then it accelerates under gravity, and on reaching the floor, which is 1.75 meters below the point where it was dropped, the ball rebounds to 1.5 meters, and the question says we need to determine the magnitude and direction of the impulse delivered to the ball by the floor. So I was explaining this, that the impulse is generally defined as the time effect of a force, which is what we have on this right-hand side. Or in other words, it is simply the change in momentum. Change in momentum, you can see that the time effect of force times delta t, in this case, the product of force times the time over which the force is applied, gives us that impulse, which is equivalent to final momentum minus initial momentum. And this is generally the change in momentum. It is the change in momentum. So this is how we define impulse. Impulse is defined as the change in momentum. Or in other words, the time effect of a force. So in different applications, you would find that when the force is applied over a longer duration for the collision, then the effect of that force is generally reduced. The effect of that force will generally be reduced. And the reverse will be true if the change in momentum occurs over a shorter period. So you then find that there is a greater impact. The impact of that force is great. So the force generally is great. So this is impulse. And now in the calculation here, it means we need to see whether we have F. We don't have F. We don't have delta T. But we have the mass, where we can find the final velocity after impact. You can find the initial velocity after impact. So that's what we need to do for this question, to find the impulse. So remember, when the ball is dropped from a height h, it has got a potential energy given by mgh, and at the point of contact with the ground, it will have a velocity which is such that the kinetic energy is equivalent to the magnitude of the potential energy. So all the potential energy has been converted to kinetic energy at that point, and hence we can find V. You could still use the vertical projectile equations, where you have height, you have initial velocity 0, you have the acceleration due to gravity, g, and that can still give you the velocity with which the ball strikes the ground. So either way, the value of v should be the same. So you could check that with an equation like Vf equals to Vi plus At. That's if you have time. But in this case, you don't have time, so you would use Vf squared equals to Vi squared plus 2As, where S is your height. You can say Ay. So A is the acceleration due to gravity, Y is the distance traversed, which is 1.75 meters. Your Vi is 0, so you can still have Vf equals to root 2A, which is the acceleration due to gravity, and Y the height. The same applies, we cancel M, divide by M both sides. We remain with GH, then multiply by 2 both sides. We have 2GH equals to V squared. And taking the square root of both sides, we've got V equals to the root of 2GH. So you can see that these two equations are the same. V is the root of 2 times the acceleration due to gravity times the height, or the vertical displacement. So we can find that velocity with which the ground is struck by the ball. And this is our initial velocity for the collision. So Vi equals to root 2G height. I'll use height, you can use Y, you can use anything there. So that's root of 2 times 9.8 times 1.75. So from the calculator, what do you get? Root 2 times 9.8 times 1.75 gives me 5.86 meters per second in the negative J. So this is downwards. So this is a vector, so it has direction. You give it with a vector. That will help you when you remember momentum is a vector. So when you do your operations on the momentum, the signs are very important. Now the final velocity is such that the initial kinetic energy is converted to is wholly converted to potential energy at the point when we reach the maximum height on rebound. So it means the new mgh again is equal to the kinetic energy after rebound. So that means half again mv. This is now the final velocity of the change in momentum from the ground on rebound. So half mv squared, which is the velocity with which the ball leaves the ground. We'll call it Vf because it's the final velocity during which the momentum change occurs. This is equal to the mass times g times the new value of the height. So we'll call it height with a head, which is given as 1.5 meters. So the same operation, remove the m's, and we have Vf squared equals to 2 times g times the new height, such that Vf is the root of 2 times 9.8 times 1.5. So if we have 1.5 in that expression, the velocity is 5.42 meters per second in the positive j. Velocity is 5.42 meters per second in the positive j. So where are we on the diagram? We are at a point where we say the velocity Vi is the velocity with which we strike the ground. Velocity Vf is the velocity with which the ball rebounds. So the change in momentum there, change in momentum is equal to mvf minus VI, which is the impulse. So this is the impulse. The mass we know, VF we have found. Where is VF? VF we have found there, positive, and VI negative. So let's apply that to the equation. Impulse, or you can want to use I, I'm sure some texts would use I, is equal to mass times VF minus VI, and the mass is 0.3 kgs. VF, we said VF is 5.42, VI is minus 5.86. So 5.42 minus negative 5.86, 42 and 86. So this gives us 3.38 kg meter per second, and the direction is in the positive J, because the 5.42 is also in the positive J. So this is 3.38 kgs meters per second. That's the impulse, the change in momentum in the upward direction, or positive y direction, or in the direction of the unit vector J. So you give that impulse also as a vector because it has magnitude and direction. So that's what we have, 3.38 there. Then the second part says estimate the time the ball is in contact with the floor and use this estimate to calculate the average force the floor exerts on the ball. So remember, this impulse is, we say it is F times delta T, which is the time that we are asked to estimate, and that should be equal to mvf minus mvi, which is our 3.38 kgs meter per second. So now we need an estimate of the time the ball stays on the ground. The time the ball stays on the ground. So if we take an estimate of about delta t, estimated to be not 0.5, but 5 milliseconds. 5 milliseconds. So for an estimate of around 5 milliseconds, impact duration, then it means force delta t equals to 3.38 and divide by delta t on both sides, where force equals to 3.38 over 5 times 10 to the negative 3. And this gives us an estimated force of that would be 700 newtons, or 7 times 10 to the 2 newtons, in the positive J direction again, in the direction, positive Y direction, or the direction of unit vector J. Okay, so that's the estimate of the impact duration for a ball bouncing from the ground. 5 milliseconds is a reasonable estimate. Okay, if you have any questions, please just say something from the chat. You can still use the same link on Teams. The platform is up and running. You can join and call in. We can hear your voice and hear what you have to say. But otherwise, we move on to the second question. Question number 2. So with question 2, a car of mass m moving at a speed v1 collides and couples with a back of a truck of mass 2m, moving initially in the same direction as the car, but at a lower speed, v2. So v1 is the speed for car 1 with mass m, and it is less than v2 is less than v1, which is the speed of car 1. And the mass of car 2 is twice the mass of car 1, such that we have the two coalescing after the collision. So the speed Vf of the two vehicles immediately after the collision will be such that by conservation of momentum, m times v1 plus m 2m times v2. So the mass of car 1 is m, the velocity is v1. The mass of car 2 is 2m, the velocity is v2. The total momentum is equal to the total final momentum, which is the total mass of the two coalesced bodies, m plus 2m, times the velocity final. So this is the equation, which is a consequence of conservation of momentum. So when the two bodies coalesce, that's an inelastic collision. Kinetic energy is not conserved. That's one thing for sure. So now with these two, we need to express the given quantities in terms of Vf. So if we factor out m, we've got m times v1 plus 2 v2 equals to m 3 Vf. So it means 1/3 V1 plus 2 V2 equals to Vf. So this is the expression. There are no numbers given there, so we just give Vf in terms of the given quantities, which is that expression. The next part says what is the change in kinetic energy of the car-truck system in the collision. So the change in kinetic energy. So already this tells you kinetic energy is not conserved, as we said. So we've got delta Ke is equal to Ke final minus Ke initial. That's the change in the kinetic energy. So the final kinetic energy is half times the total mass, m plus 2m is 3m, multiplied by Vf squared. The velocity of the two bodies there is Vf, so we have half mv squared, minus the initial kinetic energy, will be the sum of the individual kinetic energies of the two cars. So that's half of the first mass times v1 squared plus half of the second mass. The mass of the second truck is 2m times v2 squared. So that negative sign affects both. So this is 3/2 Vf squared minus, remember we expressed Vf in terms of V1 and V2 right here. So we can substitute. We could substitute, we'll do that later. So this is minus half m V1 squared plus 2 V2 squared. So I factored out half m from this squared bracket. So you factor out half m there, you remain with V1 squared plus 2 V2 squared. So now substituting for Vf, which we found in the previous expression, the one that's showing on the screen right now, we have 3/2 Vf is 1/3 V1 plus 2 V2, and this whole thing is squared, right? So the 1/3 V1 plus 2 V2 is squared minus half 3m, so this is 3m minus half m V1 squared plus 2 V2 squared. So taking the like terms or expanding the brackets, we have 3m over 2 multiplied by 1 over 9 V1 squared, or let me just take the 1/3 outside, the 1 over 9 there. Then we can now square the part in the inner bracket, V1 squared plus 4 V2 squared plus 4 V1 V2. So remember, it's V1 times the V1 from the other bracket for V1 squared, then V1 multiplies that component from the other bracket, which is 2 V1 V2, and now 2 V2 multiplies V1, we get another 2 V1 V2 to make a sum of 4 V1 V2, and 2 V2 multiplies the other 2 V2 on the other side to give 4 V2 squared. So that's how you square that bracket to get this product. Then this is minus half m V1 squared plus 2 V2 squared. So simplifying this, we've got 3 there. This is m over 6 V1 squared plus m over 6 times 4 V2 squared plus m over 6 times 4 V1 V2 minus m over 2 V1 squared minus 2m over 2 V2 squared. So now we simplify for the like terms. We have this part in V1 and that part in V1, so that will give us V1 squared m over 6 minus m over 2 plus V2 squared 4m over 6 minus 2m over 2. Then so that's the second part, then plus 4m over 6 V1 V2. Now simplifying this, this is V1 squared 6 1 m minus 3m plus V2 squared 6 again 4m minus 6m. So 6 into 6, that's 1, 1 by 4 is 4m, then 2 into 6, that's 3, 3 times 2 is 6m. So that's just putting everything in bracket into as a single fraction, plus 4m over 6 v1 v2. So this gives us minus 2m over 6, which is minus m over 3 v1 squared. This also gives us minus 2m over 6 minus m over 3 v2 squared, then plus 2 over 3 m v1 v2. So we can factor out negative m over 3 v1 squared plus v2 squared minus 2 v1 v2. So that's the expression for the change in kinetic energy, delta KE. Remember, that's what we were calculating from here. So our change in kinetic energy will be given by that expression in terms of V1 and V2. Minus m over 3 V1 squared plus V2 squared minus 2 V1 V2. Okay. So it's just a matter of giving expressions. In this case, you just do the calculation for VF, applying the conservation of momentum, make VF the subject. Then for change in kinetic energy, final kinetic energy minus initial kinetic energy, and substitute to eliminate VF from the expression. Then on simplifying it, this will be your final solution for change in kinetic energy. Okay, then we have for question number 3. Let me just check in case we could be having a question written somewhere. Okay. So I think everything is okay so far. Okay, so going to question number 3. 2 blocks are free to slide along the frictionless wooden track shown in the figure. So there is a block M1 whose lower surface or lower face is a height h above the flat surface of the wooden system. So on this wooden track, the block of mass M1, which is 5 kg, is released from the position shown at a height h, which is 5 meters above the flat part of the track. Protruding from its front end is the north pole of a strong magnet, which repels the north pole of an identical magnet embedded in the back end of block of mass M2. So you have a north pole repelling with the north pole of this block of 10 kg, given as M2, initially traced. The 2 blocks never touch. Now calculate the maximum height to which M1 rises after the elastic collision. So the first thing there is to find the velocity with which the block M1 reaches the flat surface. And we can do that using the same equation that we have been using throughout, to say all the potential energy is converted to the kinetic energy of this block. So we'll say, we'll call it, let's just call it V1, half mv1 squared is equal to mgh. So this will give us the equation V1 equals to root 2gh, such that that velocity is the root of 2 times 9.8 times height is said to be 5 meters. Two times 9.8 times 5, 9.9 meters per second in the ijk, so this is I, in the positive I direction. So this is the velocity along the horizontal when the block sliding on a frictionless wooden track reaches the bottom of that curved surface and begins to move horizontally towards M2. So this is the velocity with which basically the block collides. So this is the velocity with which the block will collide. Now, we need to find the rebound velocity, And for such a system, the two do not collide. We can use a text analysis to determine what is the velocity after collision or what is the rebound velocity for this block. The effect that is frictionless, that rebound velocity, allows us to use the rebound velocity or the rebound kinetic energy for the height, using the fact that if there is no other loss of energy, then all the kinetic energy will be converted to potential energy at the point when the block reaches its maximum height. So for this text analysis, we have a V final. So this was V initial. Let me just call it initial. The V initial, V final will be M1 minus M2 over M1 plus M2 multiplied by the V initial, such that M1 is the mass of the block, which is 5 kgs, M2 10 kgs over 5 plus 10, 15, multiplied by 9.9 meters per second. And this gives us minus 5 over 15 minus 1/3, so that's 9.9 over 3. That's negative 3.3 meters per second. So this block M1 rebounds from close to M2 with an initial velocity of 3.3 meters per second. And this velocity is what gives us the kinetic energy, which is converted wholly into potential energy when the block reaches maximum height. So half m VF squared is equal to mg times the new height. And that new height is half VF squared equals GH prima. So divide by G both sides, and we divide by G there. So H equals to VF squared over 2G, which is negative 3.3 squared divided by 2 times 9.8. And this gives us a rebound height of 0.556 meters. So our rebound height there will be 0.556 meters. Okay. So what is important is to first find the velocity with which the block M1 reaches towards M2 or reaches the flat surface of the track. And we used conservation of energy, where all the potential energy is converted to kinetic energy, and that enables us to find the velocity at the bottom of the or at the flat surface, or from where the flat surface begins. So at that point, the velocity is 9.9 meters per second, and we have this equation, which we obtain from text analysis, where we have the final velocity or the rebound velocity there being given by the difference between the masses over the sum of the masses multiplied by the approach velocity. So this will give us the rebound velocity for this system, and we can then find the height using conservation of energy again. So that's the rebound height for this question. Question number 4. For question number 4, a wheel starts from rest and rotates with constant angular acceleration to reach an angular speed of 12 radians per second in 3 seconds. Find the magnitude of the angular acceleration of the wheel and the angle in radians through which it rotates at this time interval. So we want the angular acceleration. We know that the final angular momentum is equal to the initial angular momentum plus the angular acceleration times the time squared times the time, right? So this is from final velocity equals to initial velocity plus acceleration times time. So knowing our initial velocity, W, angular velocity is 0, the final is 12 radians per second, and t is over 3 seconds. Then we substitute or first make alpha the acceleration the subject. We have W, F, omega F minus omega I equals to alpha t, and divide by t both sides. Then our acceleration is omega F minus omega I over t, where omega F we said is 12, omega I is 0, and t is 3, and this gives us 12 over 3, which is 4.00 radians per second squared. So this angular acceleration is 4 radians per second squared. And the angle in radians through which it rotates in this time interval. So the angle in radians, theta, is equal to omega I, initial velocity, times t plus half alpha t squared. So what do we get from that expression? We have already found or given assigned values to omega I. We don't have omega F, we have found alpha to be 4. And we know t. So substituting, we get 0 plus half 4 times t squared, and this gives us 18.0 radians. The angle is 18.0 radians. So those are the two parts to question number 4. I hope you guys can follow. I hope you guys can follow. So now a different one, question 5. With question 5, a wheel 2 meters in diameter lies in a vertical plane. So we have a wheel and a diameter 2 meters. lies in a vertical plane and rotates about its central axis with a constant angular acceleration of 4 radians per second squared. The wheel starts at rest at t equals to 0, and the radius vector of a point P on the rim makes an angle of 57.3 degrees with the horizontal at this time. So we would have a point, the horizontal, and that point P can be there or there. All we are interested in is to know that the angle there is 57.3 degrees. Now, at t equals to 2 seconds, find the angular speed of the wheel. So the wheel starts from rest. It means omega I equals to 0. Then t is 2 seconds. We need to find omega f. Alpha is already given. So our final is omega I plus alpha t, which is 0 plus 4 times 2, and that gives us 8 radians per second. That should be 8 radians per second for the final angular speed. Then the tangential speed. The tangential speed is like the linear speed after 2 seconds. Tangential speed is given by v equals to omega r, and this is 8 multiplied by 1. The radius, remember the diameter is 2 meters, so the radius will be 1. So omega times the radius gives us 8.00 radians. Sorry, this is now meters per second. This is now in meters per second. The tangential speed. For a radius of 1 meter, the tangential speed is 8 meters per second. Okay. Then the third part, the total acceleration. The total acceleration. So it means we have acceleration in the towards the center, which is the radial acceleration, what we call centripetal acceleration, and we also have the acceleration tangentially. So the total acceleration will be the vector sum of these two components. So the first one, centripetal acceleration, magnitude of AR equals to AC, which is given by omega squared r. Omega squared r. And that's 8.00 squared times 1 meter. This gives us 64.0 radians per second squared. Right? So this is the centripetal acceleration, which is the acceleration towards the center. For any body that's moving in that's describing a circular path, there is an acceleration which is towards the center. Okay, then the tangential one, AT, will be given by alpha times r, where alpha is the acceleration given as 4, and r is the radius 1, and this is 4.00 meters per second squared. Now, the total AT is, remember, we have these two components. We said it's rotating in that direction, so the tangential is that component, the radial is that component. So the resultant will be the total acceleration. I have tangential there, so what do? Let me just call it A without, of course the other one is tangential, so that's A tangential and AC. So the resultant is just A. The resultant is just A, or AR for resultant. So our resultant here will be the square root of AT squared plus AC squared, which is the root of 4 squared plus 64 squared. $64.12 is the total acceleration. This is the total acceleration. And the angular position, okay, so the acceleration is at an angle, arctan. So this, if this is our angle, what should we call it, phi? Then phi is arctan AT over AC. This is a 90-degree triangle because it's tangential here, so it's tan is opposite of adjacent, which is AT over AC. So the angle phi is arctan AT over AC. Remember, we have a triangle like this. Let me just redraw that triangle. This is A. This is AC. This is AT. So AT, we've just, because vectors are space invariant, we've just shifted AT from the tangent to the center, such that we also have a right angled triangle there. And the angle phi is that one, the angle that the total acceleration makes with the radius. So that angle is phi, not theta. That's phi. And arctan AT over is arctan 4 over 64. That should give us something like 4 over 64, 3.58. So phi is 3.58 to the radius at point P. At point P. So the angle that the acceleration makes is 3.58 to the radius at point P. So this acceleration, because it's a vector, we give magnitude 64.12 meters per second squared at an angle of 3.58 to the radius at point P. So we give both magnitude and direction for the acceleration. So let's see, we have WF 8 radians, 8 meters per second for the velocity, which is the tangential speed. So because it's a speed which is requested there, we're not giving directions. And we have the tangential, the total acceleration, which we just found with the magnitude and direction. And the angular position is what we need to find next. So for angular position, theta final is equal to theta initial plus omega initial t plus half alpha t squared. So when we used this expression to find the change in the position, this was like delta theta, which is theta final minus theta initial. So this is the change from the reference point. Usually if your reference is 0, then the shift in the angular position is just equivalent to the final position. So assuming your theta I reference is the 0 position, then theta final is generally equivalent to the change or to the displacement, angular displacement. So in this case, we want the final position and not the displacement. We want the final position. So theta I was 57.3 degrees, which is equivalent to 1 radian. So remember, these equations are given in radians. The unit we use here is the radian. So we have 1 radian for 57.3. You find how do you convert theta in degrees to radians? $57.3 so you can simply shift the functions on your calculator from 57.3 to give you 1 radian, but mathematically what you are simply doing there is theta in radians equals to theta in degrees times pi over 1/8 or 2 pi over 360. So for this is your conversion factor, because 180 degrees is equal to pi radians. 360 degrees is 2 pi radians. So if you have, in this case, 57.3 times pi over 1/8, you get 1.00 radians. So this shows that 57.3 is 1 radian, so we've got 1.00 plus omega initial. We said omega initial, we listed it somewhere. Omega initial is 0, t is 2 seconds, and everything else we have alpha is 4. So omega initial is 0 plus half, alpha is 4.00, and t is 2 seconds. So this is 1 plus 2 times 4, 8. This gives us 9 radians. The final position of that point P is 9 radians. So that's how we get 9 radians. So yeah, I think that's pi of 180. Thank you, Linamandla. Linamandla just gave us pi over 180 degrees. Pi over 180 degrees, which is what we used here. Okay, perfect. Great. Thank you for that contribution. I hope you guys were able to follow and everything that we have covered makes sense to you. But if you have any questions, you are free. You can just type something in the chat, just like Linamandla did, and we can look at those questions. Otherwise, for the rest of the questions that follow, let's meet again tomorrow for another session at your convenience. But if you will be available, it's okay. You can join us live. But if you will be occupied or you'll be having lectures, that's still okay. You can see the recordings will be available on both Teams and on our YouTube channel. Otherwise, from me and everyone else, this side is goodbye and have a great day.